In this lesson, we are going to find the time period of a simple harmonic motion. There are two methods. First one is called restoring force or torque method, and second one is energy method. In this lesson, we are going to learn restoring force or torque method. So this method will have some steps. The first step is finding the mean position. So you have to find the mean position. At the mean position, potential energy is minimum and force or torque is zero. So if we consider a spring block system, which is an example of a linear SHM, M is the mass, K is spring constant. When the spring is at its natural length, then it is at the mean position. Okay, if you don't know the spelling of mean position, you can call it equilibrium position. Equilibrium means net force is zero, stable equilibrium position. So now the spring is at its natural length, that is the mean position. Here potential energy is minimum, in fact equal to zero, and the force also is zero. If we consider a simple pendulum, which is an example of angular SHM, then this is the mean position. So first step is to find the mean position or stable equilibrium position. Net force at this position is zero, net torque at this position is zero, and potential energy is minimum. Here potential energy is zero, here potential energy is minimum, not equal to zero because this will be at some height. The next step is to displace the particle by a distance x in case of linear SHM, or an angle theta in case of angular SHM. So that is the next step, displace the particle by a distance x in case of linear SHM or angle theta in case of angular SHM. Once you have done this displacement, we try to find the net force in case of linear SHM on the particle in the displaced position, or net torque in case of angular SHM. Okay, net torque in the displaced position. Now first we check whether the force is trying to bring the particle to the mean position, whether the torque is trying to bring the particle to the mean position. So here the force is trying to bring the particle to the mean position, the torque is also trying to bring the particle to the mean position in this case. And after this, we check if F is proportional to minus x or torque is proportional to minus theta. So that is the requirement of SHM. In SHM, if it's linear SHM, force will be proportional to minus x. Torque will be proportional to minus theta. So once we have verified this, we know that the motion is simple harmonic. So that is the next step. Once we have proved that the motion is simple harmonic, then we can write F as minus kx and torque as minus k theta. So now we have F is proportional to minus x, torque is proportional to minus theta. So F becomes minus kx and torque becomes minus k theta. Once we have got force and torque, now we can calculate acceleration in the next step. Okay, so that we can call it step 5. Okay, so in this case acceleration will be force upon mass, so it is minus k by mx. And here acceleration is angular acceleration, that is tau by moment of inertia. So we get this as minus k by I theta. So once we have got this equation, then we realize that in SHM, acceleration is minus omega square x in linear SHM. And in angular SHM, alpha is minus omega square theta. So now we can get omega here by comparing these two equations. Here we can get omega by comparing these two equations. So therefore here omega will be root over k by m. And here omega will be root over k by I. And omega is 2 pi into frequency or 2 pi by time period. So 2 pi into frequency, 2 pi by time period. So time period here will be 2 pi root over m by k. Okay, that is 2 pi by omega. Time period is 2 pi by omega, so 2 pi root over m by k here. Here also time period will be 2 pi by omega, and that will give us 2 pi root over I by k. So this is the restoring force or torque method.